Good afternoon, everybody. I'm here to give you an introduction to neutron imaging, and I will do this alongside some examples, of course. But let me start with the facility. I'm working at the Paul Scherrer Institute, which is a national lab of Switzerland, and it's running several large-scale facilities. You see in the foreground our synchrotron, the Swiss light source, and then you see the bigger building here in the center. That's our muon neutron source, the SynQ. It's a spallation source with a proton accelerator, but we get a continuous neutron beam out. On the other side of the river, we used to have a research reactor, which is not running anymore, but we have storage of radioactive waste of Switzerland, and then energy research and nuclear safety research and biology. And here in the forest, you don't see it, we also have a free-electron laser, the Swiss FEL. So it's quite a large campus with a lot going on. But we look into the laboratory for neutron scattering and imaging. Quite a typical facility. We have the source here in the center where the proton beam shoots from below into a lead target, and then we have the typical arrangement of instruments around, and then neutron guides go into the cold instruments in the guide hall. Currently, we're considering to mirror this and also build a guide hall on the other side, on the north side, so that we can build more instruments here, as we could support this without having to build a new source. My group is running 4 instruments mainly for neutron imaging, but also for engineering diffraction. But in this talk, we will focus on neutron imaging. So we have a thermal imaging station, Neutra. We have a cold imaging station, ICON, and then we have a test station with polarized neutrons, BOA, and how we use that for imaging, I will explain quickly. So imaging is a relatively simple technique. You need a source, then you have your object, the detector, and then the radiation goes through the object and attenuates the beam. And then depending on what material there is there, you get a shadow image in different gray levels. And you can then calculate the attenuation and see the inner structure of objects. This is simply governed by Beer-Lambert's law. So we have the incoming intensity, and it gets attenuated by, we have an attenuation coefficient here in the exponent. And then, of course, the thickness of the material plays a role. But the most important is how do we get spatial resolution. Typically with a camera, you have a lens, and then you get a nice focused image in your camera, on your film, or on your digital sensor. The problem with neutrons is it's not easy to build a lens. We're working on some techniques, but currently we're still using a very simple pinhole technique. That means, as the image should here show, that we, of course, get much less intensity for our imaging than we would have if we would have a lens. But that means we need a strong source to do good imaging and to also get time resolution and stuff. So the setup is very primitive. Here you see a camera obscura. That's the same principle, just that in our case, the sample is right in front of the detector and the beam comes from the source. And then the size of the aperture that we have at the source side and the length decide on our spatial resolution. So the longer the distance that the object and the detector are from the source aperture, the better our resolution gets. The smaller our aperture is, the better the resolution gets, but the less intensity, of course, we have. And then it's important to keep the object very close to the detector, because that obviously improves our resolution as well. So that's why typically we have our object and our detector sitting quite far away from our pinhole, so several meters, typically 5 to 10 meters, to achieve a spatial resolution. The other thing that is, of course, important to achieve spatial resolution is the detector technology. Typically, we're using scintillators and then light-sensitive CCD or CMOS cameras. And you see here the evolution of spatial resolution. When I started there in around 2000, spatial resolutions were about 200-300 micrometers only. And since then, we set the journey to improve this resolution, and we made great progress. You see nicely here, like we have an exponential improvement of resolution over the years, and the latest breakthrough was when in 2016 we introduced our neutron microscope with which we now achieve resolutions of around 3-4 micrometers, which we are currently working with. But what you have to see that if we go to such high resolution, which is similar to what you have with X-rays, typically, then our samples also become very small, and that means we only have samples then of a few millimeters. And then some advantages of neutron imaging, of course, go away, because when samples are very small, you can also penetrate with X-rays and so on, and you have hard times already to get contrast. But still, we're pushing further and see what we can do. So, talking about contrast, neutrons, as you all heard, of course, throughout the course already, they interact with the nucleus, and they can be absorbed, or they can be scattered, or they can transmit. And the scattering and the absorption, they contribute to our attenuation cross-section, which together with the density of the nuclei gives the attenuation coefficient. When you now compare these to X-rays, the processes are similar. We have transmission, the X-rays can be absorbed, and they can be scattered. But the difference is that the X-rays interact, of course, with the electrons in the shell of the atoms, while the neutrons interact with the nucleus. And that gives a very different cross-sections and very different behavior. And while you do imaging, of course, also with X-rays, there are quite some cases where you need neutrons to answer your question. And the points are mainly that for many elements, neutrons provide a better penetration. That means you can look through bigger samples, thicker samples. And this is the case, for example, for many metals. You see on top a very large object. This is a motor block of a BMW. And you can penetrate this engine, and you're still sensitive to see the distribution of oil. When you run the engine, how the oil moves in this engine. You can also look through materials that are used as scintillators, or even as shielding material of X-ray. Lead, for example, is like a window material for neutrons, and other elements, heavy elements like gold, which stop X-rays very quickly. We can investigate with neutrons, and that's a typical Swiss example. Gold, jewelry, and also the jewelry industry in Switzerland wants to do additive manufacturing, so print their jewelries, and this is some first attempts to print gold, and looking at the porosity that we get there. Also there, they don't care so much about the porosity in the inside, but the porosity close to the surface where it could get visible. This is what they want to avoid, and that's where neutrons are very useful to look into such materials where X-rays are stopped immediately and cannot penetrate. On the other hand, there are some elements, some light elements, which are basically invisible for X-rays because they're so light, they have so few electrons that they have no stopping power for X-rays. But they have very high cross-section for neutrons, and this is in particular hydrogen, but also lithium, which is currently very important in batteries. So when we look for hydrogen, for example, here an example of our high resolution, a comparison of a neutron image to a microscopy. The advantage of the neutrons is, of course, we can look in the bulk of the material and we can quantify the hydrogen. And we see here nicely the hydrides forming. This is a cladding material of nuclear fuel, where hydrogen is an issue when it goes into the material because it embrittles the fuel claddings, and we don't want these fuel claddings, of course, to break. In particular, also not when the fuel gas goes for storage and so on, so not to spill out all the radioactive inventory there. So these are important studies concerning nuclear safety. But also in alternative energies, fuel cells, we use neutrons a lot because as we're so sensitive to hydrogen and can look through metals, we can look into fuel cells while they operate, and we can easily see how the water forms, how the water is transported around, and where the water accumulates and negatively affects the process of the fuel cell. And this is to optimize fuel cell technology. And finally, as I mentioned already, also lithium. Also, this is a metal hydride battery, but it works the same way for lithium. You can observe the lithium while you charge and discharge batteries, and you see how the lithium is moving between the electrodes and where it gets stuck. And also here you can optimize technology for batteries. And here you see a nice example in cultural heritage study between X-rays and neutrons. Here you have a Buddha statue, which is made of metal, and then the X-rays can partially penetrate, and you see through, but you do not see all the organic material inside, which contains a lot of hydrogen. And with neutrons, you penetrate the metal very easily, so you hardly see it, but you very well see the things contained in this statue, which is organic material, plants, and here you have a wooden column. So here you can see the complementarity of the contrast that you can achieve, and very often we therefore also combine neutron and X-ray imaging, because it's very simple to put an X-ray imaging setup into your neutron beam and measure both at the same time. Here's another illustration with a killer application, we call it. This is a bullet, where with the neutrons you see the plastic explosives here very well, which you don't see with the X-rays anymore once you penetrated the metallic capsule here. And the example also, the lead bullet can be penetrated by neutrons easily, but not by X-rays. And what you see here as well is, is with the growing number of electrons, the attenuation of X-rays is going up, so it's getting darker and darker. And with neutron, it's rather irregular. There are materials neighboring where one is a strong absorber and the next one not, and the medium one. So you have much easier time, for example, to distinguish between materials which are close to each other in the table of elements where they are similar for X-rays. So this is another application case for neutrons to distinguish such materials. And another thing that is important, and you have heard before in scattering as well, as the neutrons interact with the nucleus, they are sensitive to isotopes, and so you can distinguish isotopes, or you can use the contrast. You can influence the contrast by replacing, for example, hydrogen with deuterium, like it's done in small angle scattering, as we heard before. And applications here are again a nuclear one from the old days, where you can see the uranium enrichment in fuel pellets of nuclear fuel, and you can analyze that easily. But another application is when you want to study the water uptake in plants, then of course you have a problem, because a plant has to contain water all the time, otherwise it's dead, and it will not take up water anymore. So what do you do to see how the water is moving in the plant, how quickly it's transported? And it's very simple. You feed the plant for a short time with heavy water, so that it doesn't harm the plant, and then you can follow the heavy water, as it makes a strong contrast to the normal water, and you can follow how the plant drinks and how it takes up the water and where the water goes. And another example, we've seen the fuel cells before. You can have the same problem with fuel cells. You see the water at each instance, but you do not see which water is freshly produced and which is staying there all the time and not transported away. So you can also do the same trick in a fuel cell when you feed it for a while with deuterium gas instead of hydrogen. Then you create a contrast for this specific water from this specific time, and then you can follow this water and see if it accumulates and when it moves. And that helped us to understand the working of a fuel cell at high power, when the conventional two-phase flow models did not work anymore, and we could see how the water accumulates and then is going to the channel basically in certain flows at certain times. And we could develop a new model to understand how the water balance is working when the fuel cell is operated at high power. And this, of course, gives you answers to help you to improve the technology and the fuel cell technology. So, but when we're talking about contrast, we said in the beginning already, the contrast is not only absorption of neutrons, but it's also scattering. And here we see with some materials that we often look at, like iron and steel or copper, the absorption often plays a smaller role than the scattering. And so the question arises, can we also get sensitive to scattering and learn something from that, and not only from the integral attenuation? And you see here, for example, when you use different energies of your neutron beam or different mixes of the spectrum, then these contributions vary. That means there is a strong energy or wavelength dependence there. And when you look at the cross sections, then you see the following, that you have in particular at crystalline material like metals, you have a strong contribution of the coherent scattering from break scattering here, break diffraction, which gives you this very distinct breakage pattern. And then, of course, you have contributions from inelastic coherent and incoherent inelastic scattering, and this would be the contribution of the attenuation, which increases more or less linearly with wavelength. But that means now that when you can do imaging with wavelength resolution and you can measure these patterns, then you learn something about the crystalline features of materials. This I mentioned already. So what we can do, for example, when the position of such a breakage, so basically the crystalline lattice distance varies slightly, then we can see the strain that is on the crystal lattice. So we can map stresses and strains. And in this example, we have additive manufactured steel, and we can see how we have an increased tensile stress on the surface. And we try to counter this here in this example with laser shock peening, and we also do 3D laser shock peening. That means when we do additive manufacturing, we can do laser shock peening on layers, intermediate layers, and then continue printing. And this way, we can basically design the stress field in these materials. And what one wants to avoid is these high tensile stresses on the surface, because that leads to failure of the material under fatigue. And so we have laser shock peened half of this sample on the surface, and we see how we can turn the tensile stresses in red to compressive stresses in the surface. And that, of course, helps the fatigue resistance of the material, and we can nicely control this with such measurements. But what we can also see is different phasic, austenitic, and martensitic steel we can distinguish, and this is a quenched samples where we see the different distribution depending on the manufacture of the sample of these two steel phases. Also, it's the same material, would give the same attenuation, but due to this shift in the breakage between these two phases, here around 4 angstrom, we can easily distinguish these phases. And we can also then look at phase transformations in materials under working conditions. This is the anode of a solid electrolyte fuel cell, just this fine line here. It's a thin material. And this is a measurement done at elevated temperature under hydrogen atmosphere, so that we can see what happens to this material when there's a certain stress on it in a fuel cell, and how do the phase changes work and what happens in them. So, but we do not only see the elastic coherent scattering from the breakages, but also, for example, when the temperature changes, then the inelastic scattering contribution changes. And we see that, for example, here in the tail, after the last breakage, we have a variation in the attenuation due to the temperature, due to the energy of the movements of the atoms. And we can apply this, for example, in fuel cells. We studied for a while how fuel cells work under low temperatures. You can imagine when you want to run a car with a fuel cell and you're a cold climate, it's winter like now, what happens when the water freezes in such a fuel cell? Is your engine dead then, or what do you do? So we studied here how it comes to freezing of water in fuel cells, and how long this water can also be at minus temperatures, but still liquid, so super cooled water. And we can observe these phase changes in the fuel cell due to this inelastic contribution to the attenuation quite in detail and with spatial resolution. So we also see where things happen, when things happen, and how do they move through the cell. And then this inelastic contrast we figured we can also use when we look at battery electrolytes and their degradation. First, we can see that we can clearly distinguish different electrolytes depending on their different number of hydrogen bonds. So it's pretty clear which electrolyte we have, and then we can observe what happens to the electrolyte at different temperatures. How does it degrade when a battery is operated at low temperatures, for example? And we here see this example down here, the solidification of electrolyte. But what we see from this spectra is that it doesn't only solidify, but it's also only one component of the electrolyte that solidifies, and this area is then depleted of the other component, and this you can investigate in detail by fitting this attenuation spectra with models of molecular dynamics. And this is a field that is relatively new and that we follow. And then when we look at a real battery and we try to, we can see very clearly when we have such phase transformations in the electrolyte and the hysteresis that is in this phase transformation when we go to low temperatures and then go to higher temperatures again. And the interesting thing is we can at the same time look at the break edges and we can follow the cycling of the battery and the different lithiation phases in the battery and the influence of the battery geometry on the process, on the electrochemical process that is going on, as we have shown lately. So then this mapping of the temperature through the inelastic contrast we can also apply in metal additive manufacturing. We have built a printer with which we can print metal on the beamline. And with the inelastic contrast, we can see how the temperature evolves during printing. And you can see here how the material heats up. And then we stop the printing for a while and the material cools down. And then we continue printing and it heats up again. And then we stop again. And this is important for some processes. But you will see how this is also important for other observations that we make. So this is the printer that I mentioned that we have built in a PhD project for diffraction and imaging work. So on top you have the laser, and the laser can scan here the sample. Then we have a recoater, this green stuff here, which distributes powder, and then we do the process. And then we put this machine in our BOA beamline where we have a polarized beam. And what we want to see when we do biomaterial printing, so we print copper and steel, which is an important mixture because for applications where you want the stability of the steel, but also the conduction and heat transfer of the copper. And we want to see the phase evolution, and in particular the buildup of ferrites. And ferrites are a magnetic phase, and that means with polarized neutrons we get sensitive to this phase in particular, because when you have a ferromagnetic phase, it will depolarize the beam, and the more ferromagnetic phase, the more depolarization, and only in these places, of course, where you have the ferrite. And so this is how our setup looks like. The neutrons come here in a guide field, polarized neutrons. Then here's the printing chamber. We look into here on the sample as it is printed, and behind we have a polarization analyzer and then our imaging detector. And this is the result where you see the sample growing here over time. We integrate it over the horizontal plane so that you only see the height over time, how it grows. And the first panel up here is the temperature. And you see immediately the more copper, 68% copper, the lower is the temperature of the sample, because the copper has a good thermal conductivity. And this is the case also. We have to increase the laser power when we print the copper, because the copper reflects the light more. And you see the temperature distribution, and the temperature distribution is very important for us when we want to measure the concentration of ferritic phase, because the magnetization, of course, depends on temperature, and we need the temperature to correct the polarization signal to get a quantitative result. of the ferritic phase content, which you see in this row, and you see that we get more ferrite the more copper we have in the sample. But then we can also look into detail when we now have a scale, a logarithmic scale, which is adapted to the amount of ferrite in the sample. And we see how we print more and more ferritic phase the longer we print, and the hotter the sample gets. And also what we find is, in principle, it is the cooling rate which defines how much ferritic phase we get. So when we print on a cold surface, we will get typically more ferrite than when we print on a hot sample. And that we see nicely here, where the print stopped for a while, and that means the sample cooled down. And in that instance, we suddenly built more ferrite phase into the sample as if we continuously continue printing. Good. This was diffraction and inelastic contrast, but then there's of course also small angle scattering, and we heard about small angle scattering just in the talk before. With small angle scattering, we look at structures which are in the nanometer range. And with imaging, we have heard before, our normal spatial resolution goes down to a few micrometers, so a very different length scale. But here we're looking at the orientation of fiber structures, and this is templated cellulose, where depending on how we do the ice templating, we should get different structural orientation. So when we cool from the bottom, our cellulose nanofibers should align vertically. When we cool from the side, we expect a radial orientation of these fibers. These are centimeter-sized samples. And then when we do dark field contrast imaging, so we use a modulated beam, I have not the time to explain the full technique, but then we get sensitive to the orientation of nanostructures in our centimeter-sized samples, and we can map the orientation distribution. And what we see here, for example, in this unidirectional ice templated sample, we clearly see that all orientation is vertical, as we expect here. But then we have two different species of nanocellulose, which we cool from the side. And then we see that depending on the species, we have more or less regions where we have a radial orientation of the fibers. And then in the center, when the fibers in the orientation hit, then they will start orienting vertical again in the center. And depending on the nanocellulose, we have different sizes of regions where this happens. And this is very important, of course, to understand how this templating works, and where structures are like this, and this can be applied to many also biological materials to see on real scale, large samples, how the orientation varies throughout. And now I have one last example at the end, a very recent paper that we did, where we combine basically directly imaging and diffraction in one instrument, and we measure battery, and we want to see the lithiation phases. Depending on the thickness, we measure very thick graphite electrodes. This is to increase the energy density. And then we can map in detail the phase evolution during the lithiation and the delithiation, depending on the thickness of the electrode. And we can also see, we can then distinguish between the lithium that is actually intercalated in the graphite and the lithium that is deposited otherwise, like plated or in the solid electrolyte interface, so dead lithium. And this is a very important step in the investigation of high energy density batteries. And I think that was my last example. But if you're interested to learn more about neutron imaging, we just published this book last year on neutron imaging and advanced techniques. And take a look at it. And with that, I thank you for your attention. And I also stress that there are a lot of industrial and commercial applications of neutron imaging, for example, quality control for our European space program of rocket components. So thank you for your attention, and I'm open for questions.